Hello, in this video we're going to be talking about electric cells. What's the deal with batteries? That's basically what this topic, little subtopic covers. It's a quick one. We can pretty much cover everything we need in one little video here. At least the basics and the equation, the one equation that you will need to deal with what's going on with batteries. All right, so for the chem enthusiasts out here, here's a little image of the inside of a battery. We don't get too deep into it. There are some resources on Schoology if you're curious. We'll talk a little bit about it. But essentially, here's some of the ideas. All right, so electric cells, these are parts that make up a battery. And the idea is a cell is simply a device that takes chemical energy and turns it into electrical energy. All right. There is an electrochemical reaction that happens inside of, say, a battery, in which you have an anode and a cathode that are one is pulling electrons from the other. And this electrochemical reaction means that energy stored chemically is being turned into the flow of electrons. And so we have electricity. All right. Those two sentences there, you can spend, many weeks studying this in IB chemistry, probably, when you talk about voltaic cells. So we're looking at the very big picture here, but that's the idea: is that there's a chemical reaction that electrons get transferred, and that's what's happening inside of a battery. A battery is simply multiple cells connected together. All right, so you've seen these in the data booklet, but here's the symbol for a cell. Here is the symbol for a battery. So the idea is that a couple of cells connected together is usually what we consider a battery, because we'll talk about this a little bit, but a cell usually has a certain specific potential difference based on the metals you choose, the solution that they're in, and it's often smaller than we want, so we can connect these together, say, in series to get whatever voltage we want. All right. The picture on the first slide here kind of covers a little bit about what's going on with this chemical reaction. So again, check out Schoology's additional resources if you want to see this kind of reaction in all of its chemistry glory. The very, very basic idea with any kind of battery or cell is that you have two metals. Zinc and copper are very common ones for like a basic version of this reaction. But you have two different metals in some kind of a solution. This is what we mean by battery acid. And they're separated. So essentially what happens if we connect these two pieces of metal with a wire, hook our battery up to some kind of external circuit, let's say, then in this case, the copper is a little bit more attractive to the free electrons in both conductors than the zinc is. And so, to make a pretty long story short, if we connect these with a piece of wire, the copper will pull some of the electrons, the free electrons, from the zinc, leaving us with some positively charged zinc ions. When these solid zinc atoms lose two electrons, they will dissolve into a solution. And fun fact is these electrons kind of come in. Some of the positively charged copper ions in solution will pick up those electrons and plate themselves onto the copper. So essentially, one piece of metal is pulling electrons off of the other when I connect them with the wire, and I get the flow of current. So it's this kind of chemical reaction that's causing, say, oxidation and reduction to happen and to make these things move. All right, it does work in lots of different contexts. It's there's many different combinations of metals and different solutions that you can do this with. And in fact, you can make yourself, if you are stranded on a desert island or just want to have some fun at home, you can make yourself a potato battery. It's a thing. It's very, very simple. You can do it truly with zinc and copper. Turns out the juice in the potato has some nice acidic, potato juice inside of it, and it's got some electrolytes that essentially can work in the same way as the acid in a battery. On a small scale, you might get yourself a good half a volt, maybe a little bit more out of a potato. And if you stick a penny in one side and stick a galvanized nail on the other side, galvanized means it's coated with zinc, and then connect them with a wire, you truly will get a voltage. You'll get a potential difference. You probably need a couple potatoes strung together to light up an LED, But that's the idea, all right, is current will flow in this kind of setup. All right, so this is really a very simple version of what's going on with an electric cell inside of a battery. All right, here's some pictures just to visualize what's going on. These are the insides of some different 9-volt batteries. You can see you got a couple different styles of doing it, but there's a classic 9-volt battery, and we got 1, 2, 3, 4, 5, 6 individual cells inside of these batteries. So the idea is the type of cell we use inside of like a 9-volt will give you about a 1.5-volt potential difference. And so you get about a volt and a half from each cell. So if we want 9 volts, we just string 6 of those together and we'll get a battery. So this is what we mean when we say a battery is just a thing that consists of multiple cells. Here's another picture of the inside of a 9-volt battery in a kind of different style. All right, these things are all connected in series. And so we get 9 volts of total potential difference. So each of these is an individual cell with 2 pieces of metal essentially in some kind of acidic solution. Where I can turn that chemical energy into electrical energy. All right, so that's really the big picture of what's happening. Here's one more. This is like inside of your car battery, what it looks like. Your car battery is a 12-volt battery. So again, we have a number of different cells connected together to achieve that potential difference. Okay, there are different categories of cells. Just to the primary cell is like a disposable, like regular old AA battery or something like that. The 9-volt batteries we've been using in breadboarding. That's a primary cell. It's a cell or a battery that is used up. We use the chemical energy, and then it runs out of juice, and we have to dispose of it. Of course, there's another type which is called the secondary cell, and these are rechargeable. This means that we're reversing the chemical reaction. So many batteries in your life are secondary cells. Your phone has a rechargeable battery. Laptop has a rechargeable battery. If you have a portable power bank that you charge up and then use that to charge other stuff, and then you charge that back up, that is a secondary cell. So essentially what's happening with those is that you can reverse the chemical reaction. Whichever way the electrons naturally want to go when you connect the 2 pieces of metal with a wire, you say plug it into an outlet, you pull some juice for electricity out of the outlet and force the chemical reaction to go backwards. You take electrons and push them backwards to reverse the chemical reaction. And so analogy wise, we are rolling all of the balls back up the hill in terms of gravity. We are taking all of our charges and putting them back up at a higher potential so that we can use that potential difference again the other way. All right, so a secondary cell, we can recharge it. You plug it in, you force current to flow backwards through the cell, and in doing so, reverse the chemical reaction so you can do it all over again. All right. And we've done some practice already where we talk about an ideal battery. We'll talk about non-ideal cells and batteries now. But an ideal battery just means it's got a stable, constant potential difference across its terminals, the 2, prongs of the battery. It also means that it would always have perfect efficiency. It would take all of the energy that it's converting from chemical energy to electrical energy. It would do that perfectly with 100% efficiency, give all that energy to the, external circuit. Of course, we know that that's not possible when we have an energy conversion. And you have maybe experienced this yourself when you plug something in, running a little breadboard, running anything with electricity, it's going to heat up, it's going to get warm, the battery too. And so because there's heat, we're losing some energy, right? Okay. So one thing about real batteries is that they lose their charge over time, and because of this, the voltage of a battery will decrease over time. So really all you need to know is that the voltage supplied by a cell will drop over time as we use up the energy. All right, they do have a certain capacity, and so as you run for longer and longer, you use up your reactance, if you will, and the voltage will drop because of this. So here's just an example graph from good old Cognity. This is for a AA battery, showing what happens to a AA battery over time. So take a minute to look at the graph. It's kind of interesting, but they show just 3 different situations. So one big factor is how much current you're pulling out of your battery. All right, so if we are pulling just 20 milliamps out of the battery. Say we connect it to a 62 ohm load. That's what this is showing us. Um, that's not very much current. It's going to last us a pretty good long time, 140 hours, until it drops to about half of its potential difference, at which point it's pretty well dead. Okay, if I connect it to, say, like 3 or 4 ohms, though, and I'm pulling 275 milliamps out of the battery, that's a much higher current. It's going to use up the energy in the battery much more quickly. And after, it looks like less than 10 hours, that thing's going to be out of juice. All right, so number one, there's a certain capacity, and so I'm using more energy here if I'm pulling more current, so this is going to run out more quickly. But also, remember, the last unit is called the heating effect of electric currents. This battery is going to heat up, especially the more current I pull out. Remember, power depends on I squared R. So high current means I am going to have pretty more significant heat loss in the battery, and because of that, it's even less efficient and will run out even more quickly when I'm pulling out large currents. Okay. You can connect batteries in parallel and series. Batteries and cells often are connected in parallel and series for the reasons that we talked about in terms of what you get when you connect in series versus what you get when you connect in parallel. So the good news is the rules are, of course, exactly the same as they are for, say, resistors. So in series, voltages will add, and in parallel, currents will add. In other words, when I connect two batteries in parallel, the voltage stays the same, but current can flow out of both batteries, then, say, into my circuit. They'll combine and flow into my circuit. This is good for increasing capacity and also for decreasing what we're going to get to called internal resistance. So the other way we connect them is in series. This is what all the cells inside of the batteries we were looking at, the ways that they're connected, because this will increase voltage. If I have two 12-volt batteries and I connect them in series like so, the total voltage from here to here is 24 volts. So I can increase the voltage if I need a certain voltage here. All right. Again, the idea here, though, is that if you've got 12 volts and you're pulling it out of two different batteries at once, you have more capacity. There's less resistance. Here's something you'll see sometimes. The IB doesn't do this very often, but in your everyday life, you're likely to run across this. We often measure the capacity of a battery in something like amp hours. And an amp hour, think about the units. The units themselves work out a little bit funky, but an amp we know is a coulomb per second, and then we multiply it by an hour. We're multiplying charge per time by time, which means this is a roundabout way to measure the total charge stored inside of a battery. So, of course, if I connect two batteries together and you keep their voltage the same, I'm essentially doubling my capacity because each battery has a capacity maybe of 100, right? But if I connect them in series, I'm pulling all of that energy out of through them together with a higher voltage, so the capacity stays the same. Okay, and the big topic for this, the big idea for this topic is internal resistance. This is the math you will be mostly doing when it comes to non-ideal batteries and cells, because, of course, there is no perfect battery. When you pull energy out of a battery, you're going to lose energy because of heat. All right, a battery is a physical thing. Those little pieces of metal, the stuff that it flows through, when current flows through it, it's going to heat up the contents of the battery, and so you will definitely lose some energy. We model this as an internal resistance, we call it. So we say all cells have an internal resistance to explain this heat loss. Really, we're modeling power equals I squared R, and we're saying, okay, the amount of energy that we lose every second through the battery, we treat that as though it's due to a little internal resistor. So the model that we're going to use is simplifies things a whole lot. Is we pretend that inside of a battery there's a perfect ideal little cell that has exactly the voltage that we want, and connected to a little baby R resistor. All right, so this is the internal resistance we're talking about. So we'll look at kind of how this works, but this is the picture we're going to have of a non-ideal battery. Ideal cell connected to an internal resistance. Okay. Another definition that we've seen in some of our problems is EMF. EMF, we've said, is more or less the voltage of the battery, which is pretty close. It is definitely measured in volts. Officially, it has to do with the energy being provided by the battery. Here's the definition of EMF. You do want to get this one down. Yeah, Abby likes this one. All right, so EMF is work per unit charge, of course, because it's measured in volts, so it's measured in joules per coulomb, as always. And in this case, when we're talking about joules, we're talking about the work that the battery does to run the circuit that it's connected to. So you can think of it like this. If you have a 12-volt battery, that means 12 joules per coulomb. That means for every coulomb of charge passing through the battery does 12 joules of work on the charges. And it does that by converting the chemical energy to electrical energy. All right, and another fun little fact here is that EMF stands for electromotive force. This is another admittedly confusing one because it is definitely not a force. It's not measured in newtons, it's volts. We measure EMF in volts. So way back in the day, they called it electromotive force. They liked the way EMF sounded, I guess, so we stuck with it. All right, so you want to know that's what it stands for. It's just not actually a force. Don't let that confuse you and make you think that it's like a vector push or pull that you measure in newtons. That is definitely not the case. All right, and there's another little thing, but it's electromotive force. You might, especially when we get later in the course, be tempted to call it like electromagnetic force or something. That's a whole different thing. All right, so electromotive force is what we call it. Yeah, another weird one. Okay, let's set up an equation, the data booklet equation that will give us what we need here. Here's where it comes from. It is a great exercise for you to try, so go ahead and pause the video and try this. Write me a Kirchhoff's voltage law equation for this circuit, our simple circuit with their battery connected to an external resistance, capital R. You go ahead, write a voltage law loop equation for this circuit here. Okay, hopefully you gave it a shot. All right, remember the process with Kirchhoff's law. We want to first draw our current. Now this is a simple one, it's just one loop, so I'm pretty sure current's flowing this way. Although honestly, if you guessed the other way, it would totally work out for you. All right, but the current is flowing in this direction for sure. Next step is I want to label my pluses and minuses. So remember our rules here that the get something. Let's go green. All right. Remember the rules here. For a battery or a cell, it's always set. The long side is positive. The short side is negative. Okay. But so for a resistor, the side that the current flows into is positive. The side that it flows out of is negative. So my pluses and minuses will look like this. And now I can do a loop. I can choose any old loop I want to go through and analyze the circuit. Remember, the loop is not necessarily the same thing as whatever's happening with current. So just to show that idea, I'm going to like make my loop start here and I'm going to go around like this. Why not? So I can start over here and say, okay, I'm just going to start here and trace my pencil around the loop. And whenever I go through a component, I add or subtract its voltage. And the sum of all of the voltages, no matter which way I trace and whatever loop I pick, should always be equal to 0. Okay. So if I come over here and go through the loop from minus to plus, that's a gain. So the first thing I pass through is this little resistor. So I want to add the voltage across the little resistor. And remember, to find voltage across a resistor, I'm using the equation V equals IR. All right, so the current flowing through my little baby internal resistance, little r, is I times little r. Then I come around like this. I flow through my big resistor. That's the whole rest of the circuit. So that's the total resistance of my circuit. Again, from minus to plus, it's a gain of I times big R. That's the voltage across this big R, also V here. And then I come through my cell in here from plus to minus. So I'm going to subtract the EMF of this cell. And now I'm back to where I started. So I set it equal to 0. All right. So something like this, if I do the loop the other way, I get something like this equation here. And notice, no matter which way you do it, you come to this same statement. So Kirchhoff's law works every which way. All right, but here's this statement that we get. EMF is equal to I times big R plus I times little r. I could factor out an I just to be fancy, and that will give you my data booklet equation. All right, so this is the one and only data booklet equation in topic 5.3. Covers everything you need. And here's what we got. All right, this squiggly looking E, it's officially the Greek letter epsilon. That's for EMF measured in volts. I is the current in the circuit, R is the total resistance of the external circuit, so everything that's not the battery, and little r is the internal resistance of the battery itself, of course, both measured in ohms for resistance, right? One thing you want to be able to do with this equation, I'm going to show you here, is get it in terms of V, which we're going to have a name for. We're going to call it the potential difference of the battery, basically. We're going to call it terminal potential difference. So this V over here in look at this diagram and think about what you would measure on the multimeter. It is measuring the voltage really across the battery between points A and B. All right, so this is essentially, we're measuring the voltage across our external resistance, which is the same as the voltage across the battery itself. And so if I cared about the voltage across the battery, I would want to keep in mind that V equals I times a big R, because that's the R I'm connected to. So one thing you can do, and we'll need to do with this equation, is sort of factor this back in, and from the data booklet to get I times big R, and notice that that is V. All right, so if I solve this for V, I get this equation. This is a really useful version of the data booklet equation that you're going to want to be able to do. You might even want to annotate your data booklet with this version of the equation, but of course you'll need to practice it so that when you have a fresh, clean data booklet, you can do this and get to this point, because it's very useful for reasons we'll look at in 1 second. Okay, so we call big V terminal potential difference. It's the potential difference across the terminals of a battery. What we can see is that it's definitely going to be less than the EMF, because it's EMF minus I times R. So if current is flowing, the voltage across the battery is less than the EMF. And in fact, the more current that's flowing, the lower the voltage is. All right. Get your turn on your car's engine with the headlights on. You will notice this as you pull a whole bunch of current to get the engine started. The lights will dim because the voltage of your battery drops a lot, because you pull a lot of current out in a couple seconds to get it going. All right, so if I'm thinking about this equation, if I equals 0, then voltage equals EMF. So one way we say that is that the EMF is the open circuit potential difference across the terminals of my battery. So it's a potential difference when no current is flowing. All right. All right, and last thing, you can try this. What would a graph of voltage versus current look like? Use that same equation. Take a look at this. Try and sketch this out in your notes. See if you can picture what it's going to look like. What would a graph of V versus I look like? Think about what format, math-wise, this equation takes. Try it. Okay, hopefully you got something like this. This is a linear equation. It really is, all right? It's like y equals mx plus b. I guess it's really like y equals b minus xm, but good enough. I could rewrite it if I really wanted, like this, if this helps you see it better. All right, so it's definitely a linear equation where the intercept is equal to EMF and the slope is equal to negative little r, negative internal resistance. So this is something you will do and could do, is make this graph. You could pull a bunch of different currents out of a battery, measure the voltage across the battery at those different currents, plot them, and you would see that the y-intercept is equal to your EMF, and the slope of that line is equal to negative r. So you could experimentally find these things. Heck, you will experimentally find these things using that graph. So make sure you can do this. All right, you're going to do this in an experiment, and you will almost, well, you'll very likely see it on the IB exams. All right. So there you go. That's the big equation. That's a good bit of info on cells, but that's everything for the cells subtopic. So we will practice with it. We will do some experiments and dig into this equation from every angle. So we'll have a good time. All right. Have fun.